In this video, we're going to look at the trigonometric formulas, or at least some of them. We're going to look at the sum and difference formulas, the double angle formulas, power reducing, and the half angle formulas. There are some others, like the product sum and the sum to product, but I want to concentrate on these right now. These are kind of the basics. They can lead us to the others. So just kind of look through these very briefly. We can see that these only deal with sine, cosine, and tangent. We will have to potentially find the cosecant, secant, cotangent of other values. But we can use our, what other things that we know about trig functions, for example, the reciprocal identities to do that. So we'll look at examples with those later on. But the other thing we notice in some of these is we see some plus minus signs, and especially in the sum and difference here, we're not going to use both. The plus minus is just indicating a choice. So for instance, if we have two angles being added, we're going to use the top symbol here. That would mean we use the top symbol there, or addition. If we have two angles being subtracted, we would use the subtraction over here. Cosine, we see the exact opposite is true. So if we say have something like 30 plus 45, well then we're going to use the minus symbol over here. So the order of the symbols makes a difference. The plus minus is not the same as a minus plus. If we start with the top symbol, we use the top symbol on the right hand side. If we start with the bottom symbol, we use the bottom symbol on the right hand side. So notice the tangent actually kind of splits. If you start with the positive, you use positive on top, but use the negative on the bottom. Negative to start, negative on top, positive on the bottom. So that is one thing to be aware of. We want to only use one sign. We have to make that choice. Then we see that plus minus appear again over here in the half angle formulas. We see the plus minus in front of the square root. And we'll talk about why that plus minus arises in these. But again, we have to make a choice. And so the way we're going to make that choice here is based on where that alpha over 2 is. And so again, we'll see examples of that as we go through the video. So what I want to do first is just make it very clear, really try and stress why we need these formulas. So if I have something, say, sine of 2x, one of the most common mistakes I see is that students will say, well, I can just pull that 2 to the outside and write this as 2 sine x. That is not how trig functions work. That's not how any function works, right? If we have the square root of 18, I know that's the square root of 2 times 9. I can't just arbitrarily pull that 2 to the outside of the function and say the square root of 9 is 3. That wouldn't be true. Completely false. We're not allowed to just pull things out of functions until we apply the function's ideas or identities to them. So for instance, I can take the 9 out as a 3 because I know that's how a square root works. That's its property. I can't just pull things out of trig functions, or if I see sine of x plus y, I can't write that as sine x plus sine y. The same way I couldn't write the square root of x plus y as the square root of x plus the square root of y. So these formulas, what they allow me to do, notice all of them, we're manipulating the angle, with the exception of the power reducing, they manipulate the function itself. But the sum and difference, double angle, half angle, they allow us to manipulate the angle to change that angle to something different. And so they're going to be very useful when we're working on solving trig equations, when we're working on verifying trig function or trig equations, and then they're going to be useful down the road in calculus too. So speaking of calculus, for trig, usually I require students to know some but not all of these formulas. And so maybe I would give you the one set of the 4, and I would expect you to know the rest. Well, for calculus, we have to use all of these at any given time, and so we have to be aware and we have to know how to get to all of them. So the sum and difference, these are kind of at the heart of all the other formulas. I'm going to show you how we can go for the sum and difference formula and get to the other formulas. So let me start with the double angle formula. We do have to know the sum and difference. I'll stress that. Double angle, let's start with the sine of 2 theta. Well, if I work purely inside the parentheses, as long as I don't try and pull the 2 outside, I can work inside the parentheses, and I know what 2 times something means. It means there are 2 of them there. So I haven't pulled anything out, I haven't split apart the trig function, I've just manipulated the angle on the inside of the function. Well, if I see theta plus theta, that's a lot like a sum. Well, we have a sum formula for that. And so here's where we're going to get to that choice, plus or minus. Well, because I have a plus here, I'm going to use the plus on this side as well. I'm going to use those top symbols. So we could write this as sine of theta, because alpha in this case is just theta. Beta is also theta, so we'll have cosine of theta plus cosine of alpha, which we already said was theta, sine of theta, which we already, of beta rather, which we said was theta, because alpha and beta are all thetas. If we look at these two right now, these are the same, sine, cosine, cosine, sine. The commutative property says these are the same term, so we can add those together and say this is 2 sine theta, cosine theta. So we can do these for any of our double angle formulas. So let me do it for cosine as well, and I'll let you work on the tangent on your own. We see cosine of 2 theta. Well, again, we can express that as cosine of theta plus theta. And so then we'll use our sum formula, which says we can write this as cosine alpha, cosine beta, or because alpha and beta are both thetas, cosine alpha, cosine theta, cosine theta. But then here, because we started with plus, we have to use the opposite sign, the one on top, the minus sine theta, sine theta. And so when we multiply these things together, finish that out. If we multiply cosine by cosine, that is just a cosine squared. Sine is sine squared. And so there's our double angle formula. Okay, sine squared minus sine squared of theta. But notice there are two other versions of it, and where are those coming from? Well, the second we see a squared, probably in the back of our minds, Pythagorean identity is jumping out at us. And so if I wanted to have this thing purely in terms of cosine, what I could do is I could come back in here and I could say, well, let's replace that sine squared with a 1 minus cosine squared. And so I have to remember to distribute that negative. I get a minus 1 plus cosine squared theta. Well, now there's two of those cosine squares, so we'll have 2 cosine squared theta minus 1. And so, again, we started with one of the identities and we got to another one. That's the second one sitting right there. And so we could do the same thing for the sine if we just did replace the cosine squared with the 1 minus sine squared. So again, I'll leave that one for you guys to do on your own. But we can see how we're generating these double angle formulas from the sum and difference. Let's move over to the power reducing. So sometimes it's helpful to reduce the power on a trig function. Notice this set does not manipulate the angle, it manipulates the function itself. And so we're going to use something we already knew. And if we think about how to reduce a power, where do we see some powers come in? Well, they're coming in right here in this double angle formula for cosine, just the one for cosine. So let me clear a little space. Let's show this first one, the sine of sine squared of theta is equal to 1 minus cosine 2 theta. So I'm going to look at my cosine 2 theta, and where do I see just the sine? Notice I don't want to compare it to the cosine squared. I just want the sine. Well, that's this one right here. Let me write down that identity right now. Cosine 2 theta is equal to 1 minus 2 sine squared theta. I want to reduce the sine's exponent, meaning I want to get this sine squared by itself. So if we think about how to do that, well, I'm going to subtract my 1 over. We'll have cosine 2 theta minus 1 is equal to negative 2 sine squared theta. And then I'm going to divide by the negative 2. And just to clean it up a little bit, we can see the 2's cancel on the right hand side, but on this left hand side, I'm going to divide out the negatives just to make it a little bit cleaner. And so I'm also going to move the positive term, because if we divide the negative 1 by the negative 2, it becomes positive. I'm going to move that to the front. The cosine becomes negative. And that has to be equal to sine squared theta. And we can find the cosine the exact same way. Now the tangent squared is going to be a tiny bit different on this one, because we never saw tangent squared in our double angle formulas. We've never seen it anywhere except for the Pythagorean identities, which we want to convert it to a lesser power, not just a different power, not just a secant squared. But we know that tangent squared is always, or tangent is always just sine over cosine. So if we divide these two things right here, multiply by the reciprocal, the 2's will cancel, you'd have 1 minus cosine 2 theta over 1 plus cosine 2 theta. That's another handy way to get to the tangent a lot of times. Finally, I want to get the half angle formulas. And so the half angle formula allows me to take an angle that's been halved and expand it back up to the whole. And we'll see applications of all of these in just a minute. So to do this, if I compare where I see already that I have twice one angle on one side and just the angle on the other side to get that idea of halving. somewhere in there. I see that 1 in the power reducing. I also saw it in the double angle, and it doesn't matter which one we use to derive the half angle because the power reducing came from the double angle, so obviously they're coming from the same place. I think it's easiest if we use this power reducing, so I'm going to use the power reducing to generate the sine of alpha over 2. So right now, we don't quite have an alpha over 2 here, but we do see that this is half of the 2 theta. So what I'm going to do is I'm going to make a replacement. I'm going to say, let's call theta alpha over 2. And so if we think about what that means for 2 theta, that would have to be equal to alpha. So let me replace that in my double angle formula, and I'm going to rewrite the sine squared on the left-hand side just to have it over there. So sine squared of alpha over 2 is going to be equal to 1 minus cosine of alpha over 2. We haven't changed anything, we just kind of reparameterized it. We renamed the angle and we said, hey, let this theta equal alpha over 2. Well, I don't care about the sine squared this time. I want it to just be a sine. I want to see what happens to the alpha over 2. And so I need to get rid of the squared, which means I'm going to take the square root. And of course, anytime I take a square root, I have to put that plus minus in front. And so that's what gives us the sine of alpha over 2 equals the plus minus square root of 1 minus cosine alpha over 2. The same thing we see here. But remember what I said, we're not going to leave that plus minus in front when we're doing an actual problem. We have to think about where is this angle actually, which quadrant was this in. And so we'll see examples of how we're going to apply that in just a few minutes. And so again, we could do that for all of the formulas we could generate all these formulas from our power reducing or from our double angles. The tangent, easiest way to do that. Again, we can just divide the sine by the cosine. Notice we have 3 different forms of the tangent. Well, it all comes from rationalizing this thing. So we could multiply by the 1 minus cosine under the square root. That gives us Pythagorean identity. We can simplify. It all derives from Pythagorean identities and from rationalizing this fraction. So let's take a look at some examples. Let's find sine of 75 degrees. So what I need to think about, and I want to find the exact value for all of these, what I need to think about are what angles do I know the exact values for? So 30 degrees, 45 degrees, 60 degrees, 90 degrees, or any coterminal angle or any reference angle based on those, or using those as reference angles and angle we can base on those. Can I combine 2 of those or one of those halved to get this 75 degrees? Well, 75 I know is just 30 plus 45. It's not the only way we could do it. I could have also written it as the sine of, could have used subtraction, and we could have said 120 minus 45. (120 minus 45 would have also given us 75. So that is another possibility. Both we should see give us the same exact answer. So let's see if that's true. I'm going to work with this middle one first, the sine of 30 plus 45. And again, these aren't the only 2 ways. There's infinitely many ways we could do it. But let's see if these 2 in fact give us the same answer. So I'm going to have to use my sum and difference formula. And sine, if I use a plus, I'm going to use a plus here. So I'm going to have sine of 30 cosine of 45, and then I'm going to have a plus cosine 30 sine 45. And sine of 30 I know is 1/2. Cosine of 45 is root 2 over 2. Cosine 30 is root 3 over 2. And cosine 45 is root 2 over 2. And so when we multiply these things together, we get root 2 over 4 plus root 6 over 4. And because they have the same denominator, I could write that as root 2 plus root 6 over 4. And that's my answer. Now, we said just a second ago, it should work out to be the same as if I'd done the 120 minus 45. And again, infinitely many possibilities we could use here. So let's see what happens when we would do this portion in green. So we get sine of the 120 cosine 45. Then we're going to have this time the minus. We'll have a cosine of 120 sine of the 45. Sine of 120, well, the reference angle there, we're thinking about how far off the x-axis it is. It's 60 degrees off the x-axis. That means sine of 120 is going to be root 3 over 2. And because it is in the second quadrant, it's a positive. Cosine of 45 is root 2 over 2. Then we're going to have that minus. Cosine of 120, the reference angle there is 60 as well, so that gives us 1/2, but because it is in the second quadrant, we get a negative 1/2. And 45, sine of 45 gives us root 2 over 2. Very, very similar values. Of course, they're going to be similar because it's all based on 30 and 45 and 60. They're all kind of the same things. But the signs are a little different at first. But notice when we multiply those two negatives together, we're back to the positive root 2 over 4. And so we have root 6 plus root 2 over 4, which is the exact same as what we just got, what we got just a second ago. They're in the opposite order, but we know that addition is commutative, so it has to be the same thing. We, of course, get the same values. It doesn't matter how we write them, as long as we have two numbers that do, in fact, add or subtract to give us that 75. Now, there may have been another way you recognize to do this one besides just adding and subtracting values. We could have also taken half of a value to get to 75. So let me rewrite my problem. We had sine 75 degrees. And we want to think to ourselves, half of what would give us 75? And another way to think about that, half of what, or I can call it half of x, is equal to 75. Well, if we want to solve that that equation, we could just multiply the 2 to the other side, and so we'd see that we should have 150 over here. And so, with that in mind, let's figure out what this would give us. Clear this away for a second. All right, so now let's see what the half angle formula tells me. Half angle formula says sine of alpha over 2 plus minus square root of 1 minus cosine alpha over 2. Well, here's where we have to make that decision, plus minus. I'm not going to look at the 150 yet. The 150 is not what I'm looking at. I'm looking at sine of 75. Well, which quadrant is 75 degrees in? That is in the first quadrant, and sine is positive in the first quadrant. So I'm going to keep it as a positive or just not write anything in front. Then we come to the inside of our square root. We have the 1 minus cosine of alpha. So 1 minus cosine, and alpha is the thing that we had before we divided it by 2, so this number right here. We're not actually trying to find the sine of 150, we're trying to find the sine of 75, but 75 is 150 over 2, so what we had before we divide by 2 is the 150. And so now we just need to simplify this. Well, 150 degrees has a reference angle of 30 degrees. It is in the second quadrant, meaning it's going to be a negative. And cosine of 30 degrees is root 3 over 2. Let me clean that up just a second. That's a 3 in there. And that whole thing is still over 2, the square root, of course, going over the whole fraction. So I see I have a fraction. I never like that, and so the easiest way to get rid of fractions and fractions is to multiply by the reciprocal of the denominator, or multiply by the common denominator across the whole fraction, which would be that 2. So if I multiply by 2, I'd have 2 minus, well, really turns into a plus, root 3 over 4. So I multiplied everything by 2 to get rid of the 2 in this fraction. And now cleaning it up just a little bit more, I can take the square root of 4 very easily, so we'd have square root of 2 plus root 3, and then it's all over now at 2 because I took the square root of that denominator. Now, that looks very, very different than what we found just a second ago, and those answers are going to appear very different. And so if you're asked to calculate it one way or the other, it's important that we follow those instructions. If it wants us to use a half angle, make sure you're using the half angle. If you want to use the sum and difference, make sure you use sum and difference, because it is obvious to your grader which method you've used. But actually, if you were to type this into the calculator and our previous answer into the calculator, you'd see that you'd have the exact same answer. Let's find the cosine of 5 pi over 8. Now in the last one we had the choice of sum, difference, or a half angle. That is not always true. But think about the sum and differences. When they give us unique values is when we're adding thirds and fourths or sixths and fourths. Those will be unique things that we don't see on the unit circle. If we're just adding thirds and sixths, well, the common denominator between those is just 6, and so that's not going to give us anything new. We're adding halves and fourths or halves and sixths, same story. So the 90 degrees, 180 degrees, if we're adding those to 45 degrees, again, nothing new. So when we're adding these denominators here or here, and so that's why I always start with the pi over 4, the 45 degrees, because it gives me, I know that has to be involved if I'm going to have a sum. So if I think about pi over 8, well, common denominator for pi over 8, I'd have to add fourths and eighths, and eighths I still don't know how to find a pi over 8. And so for this one, I'm going to have to use a half angle, and it should be pretty obvious that 8 is twice 4, and so somehow I could use the pi over 4s to get to my pi over 8. So we can use kind of the same trick we did just a second ago, where I'm thinking, well, what half of what is going to give me 5 pi over 8? And so if we want to solve this equation, we'd multiply by the 2, and we'd see we get 5 pi over 4. And so that will allow me to calculate based on my half angle formula. So again, let's go back and recap that half angle formula right up here. Cosine of alpha over 2 plus minus square root 1 plus cosine alpha over 2. So the only difference from the sign is the plus here. The plus minus, we need to think about that to start with. And so again, we're not looking here, I'm looking at the 5 pi over 8. So what quadrant is 5 pi over 8 in? That is in the second quadrant. And is cosine positive or negative in the second quadrant? It is negative. So I'm going to start off with a negative. Then I come to my square root. I have 1 plus cosine. Now I use the 5 pi over 4. And this thing is still over 2. So I have the negative in front because of the angle with 5 pi over 8 in the second quadrant. If I look at cosine of 5 pi over 4, we're going to have to evaluate that inside. 5 pi over 4 is in the third quadrant, so that is going to give us a negative as well. That's not going to be the same sign as the front necessarily. These two signs can disagree. This is from the initial angle. This sign is because we had the 5 pi over 4. What we had before is halved. So these two things do not have to agree. I'm going to multiply by my 2 just like I did before. I'll have 2 minus square root of 2 over 4. And just like I did a second ago, I need to take the square root of that, and I should get a 2 there. I want to do one last example because I do want to show you what we would do with secant or one of the reciprocals. So let's say we had secant of 15 degrees. This is back to one of those that I could use a half angle or I could use sum and difference. So because I've done 2 half angles, I'll do another sum and difference. I can find 15 by writing that as 45 minus 30. But that doesn't really help me because if I go all the way back up here, I don't have a sum and difference formula that deals with secant. But I do know that secant is the reciprocal of cosine. So I can write this as 1 over cosine of 45 minus 30. Or another way we could handle it is we could just find this cosine of 45 minus 30 and then just stick it under the 1 or flip it after the fact. And that's what I'm going to do. So I'm not going to write it equals going to this next line. I'm going to solve this cosine of 45 minus 30 just so I don't have to write that over 1 each time. We'll figure this one out and then we will we'll take its reciprocal to get back to what we wanted to know, the secant. So cosines sum difference formula, we have cosine of the first angle, cosine 45, cosine at the second angle, 30. We switch the sign for cosine, so then we're going to have plus sine of 45, sine of 30. And if I clean these up, cosine of 45 degrees is root 2 over 2. Cosine of 30 is root 3 over 2. Sine of 45, root 2 over 2. Sine of 30 is 1/2. And so we get a root 6 over 4 plus root 2 over 4. Looking very similar to that very first example we did together. Just because, again, we're circling the same values, the 45s, 30s, 60s, giving us kind of the same values. The difference is we're not done. Now we have to go back and think, well, we needed this as a reciprocal. So I'm just going to flip this fraction right over. I'm going to put the 4 on top. I'm going to put it over the root 6 plus root 2. Depending on if you're asked to rationalize, you might need to rationalize this. I'm not going to bother rationalizing for right now. So we have now covered examples of the sum and difference, the half angle. Now the reason we didn't really do a whole lot with the power reducing is for this sort of exercise it's not real valuable. So if I have, say, sine squared of 30 degrees, well, there's no reason I can't just say sine of 30 degrees is 1/2 and then square it and get 1/4. I don't need to apply that extra power reducing because it's just not important. Double angles, they're not going to get me anything new because if I double anything that I already knew, say doubling 30 gets me 60, doubling 45 gets me 90, get nothing new. So not that these aren't important, they are going to be important. They're going to be important in our verifications and other applications later on in calculus. Just for this sort of exercise, I didn't bother doing any examples because they don't get us anything new.